Let us practice creating classes with a desired behavior. We want to create a class that represents a sock drawer. The idea here is that we would like to be able to throw socks into the drawer one by one as if they were fishes essentially. And then we would like to be able to ask the drawer, hey drawer, which pairs of socks of the same color are available? And then we want to be able to ask if we can get a pair of a specific color and subtract the two corresponding socks from the drawer. So our initial operations that we want to implement are add sock. This adds a sock of a given color. Get pair. This asks whether the pair is available of a specific color, and if so, decrements the number of socks of that color in the drawer by 2. And available colors, that gives us a list of available colors. So if we had the class as per our wishes, we would be able to write code like this. We would be able to create a sock drawer, add into it a red sock, then a green sock, and then another red sock. Then we will be able to get the set of available colors. It's a set because we don't particularly care about the order. We would be able to use the random package to pick a random color out of the available ones. Okay? And then we would be able to pick a pair of socks, a right sock, but it should really be a pair of socks of that particular color. Sock in this case would be a boolean that tells us about the availability of socks of that color. And this operation would also decrement the number of available socks. It is often a useful exercise and a recommended one to pretend that you have already the object of the type you want, and to focus on which methods you should be designing and how you would use it in practice. Okay, it's better to do this actually before you write all the code for the implementation, so that you can decide whether the object is easy to use and is as you want it before you actually spend a lot of time coding. Now in this case, let us try to do a very simple implementation first. The simplest idea is to keep the drawer as a list of all the colors, right? So just as you can throw the socks into the drawer at random, then when we add the socks to our sock drawer, we will be simply appending the color of the sock to this list of called as self.drawer. Okay? Unfortunately, the code for establishing whether you can get a pair is slightly less pleasant as a result. So if you are wondering whether you can get a pair of socks of a certain color, and if so, remove it, the code looks like this. First, I need to check if you have at least 2 socks of that color in the drawer. I do it via these. So I use the count method of a list, which counts how many elements are equal to a given value. And if I say if self-drawer count of color is greater than or equal to 2, then I have a pair of socks of that color, and I can remove the color twice, because I have to remove at least exactly 2 socks of that color actually, and then I return true. And if the if is false, so that is if I don't have at least 2 socks of that color, I return false. The other method is available colors. Notice that it's a property, so I can call it without the pair of open close parentheses, right? I can just say my sock drawer dot available colors. And so it's implemented as follows. I make an empty set of colors, and then I want to fill this set with all the colors for which I have at least 2 socks. So again, the solution is not particularly elegant. We see how the decision of representing the state of the drawer in a very simple way as a list is causing our code to be perhaps not the most elegant for the implementation of the methods. There is sometimes a trade-off between the simplicity of the representation of what is stored into an object and the simplicity of the methods that operate on that storage. So let's look at how to compute the available colors. I initialize colors to an empty set, and then I go over all the colors in the drawer. If that color appears at least twice, then I add it to the set of colors, and I return the set of colors. You see, I very heavily rely on the fact that colors here is a set and not a list, because obviously If a color appears at least twice in the list, it will be added at least twice to the set. So it's important it's a set. Okay? So if I use this definition, I can give it a spin with our intended use, and indeed it works. And we should also see that after I get this pair of red socks, because they had only 2 original red socks, there shouldn't be any more available colors. Okay, so this works. Let us return to our implementation of the sock drawer. What is really not incredibly nice is how we implement the drawer itself as a list. Okay? The point is that if we have a lot of socks of the same color, it's like counting in unary. If we have like 13 red socks, we need to store in that list red, 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 red 13 times. We can clearly do better. The idea is to use a dictionary that maps the color to how many socks we have of that color. Obviously with the idea that if we have no socks of a certain color, say black, then we don't need to have an entry in the dictionary for black socks. So what we want essentially is a dictionary such that when something is not in it, it has essentially a value of 0. And there is a way to do that in Python. It's called a default dictionary, default dict. Default dicts are dictionaries in which if the element is not found, they have a certain default. So let me import default dict from collections and define D as a default dictionary of integer. Okay, if I do this, then when an element is not found, you see D is empty because I have just created it. Let me show you. D is empty now. Okay, so it's a default dictionary of integers but is empty. And when an element is not found, it will tell me 0. It will not cause an error. So I can write also code like this, D of red plus equals 2. Because when it tries to read red in order to increment, it will get a value of 0. And if I do the increment, the following print will tell me that D of red has value 2 and D of green, because I never defined the entry for green, will still be 0. Okay? You can create a default dictionaries of any other types. You can look at the documentation. For example, if you wrote a string here, you would have a default dictionary that gives you an empty string when the element is not found. And you can also have other choices of defaults. But this is good enough for our purpose. And so I can write a much nicer sock drawer as follows. This I call it smart drawer. And the socks, I keep it as a default dictionary of int. You know, one of these things that are dictionaries, the intent is for the dictionary to map from color to number of socks of that color. So when I add a sock of a given color, all I need to write is a self socks of color plus equals 1. I do not need to worry whether I have already some socks of that color, because this dictionary is robust to colors not being found. The default is going to be 0. If I want to get a pair of socks, again the code is quite pleasant. I can just check if I have more than one, that is at least 2, socks of that given color. If so, I decrement it by 2 and I return true, else I return false. Also, the code for picking out the available colors is quite pleasant. I can simply say return the set consists of all the colors C for Cn in self socks items. You know, this is a way to iterate over the key value pairs, and the key value pairs are a color and a number if the number is greater than 1. So this set comprehension, similar to a list comprehension, returns all the colors such that the associated integer in the self socks dictionary is greater than 1. All the socks of which I have at least 2 pairs. And this will work as well. So let us take a small digression. Imagine that we have a dictionary, D1, that maps, say, strings to numbers. For example, red to 2 and green to 1. Now consider another dictionary, D2. This one can map red to 3 and blue to 6. Okay, so these you can think of them as functions from strings to real numbers, if you will. Or in general, you don't care particularly that these are strings, from some key space to real numbers. To make a comparison, let me draw two functions that go from numbers to numbers. Okay, I can have, for example, f1 that says that the result is equal to, let's assume that I call this x and I call this y to write them more simply. Okay, this is y is equal to x squared. This is a function, and another function can be y is equal to x plus 1. Okay, so if I give you two such mappings from reals to reals, if I ask you what is f1 plus f2, well, you can add functions, right? And this is the function whose value is the sum of those two values. So the function would be defined by y is equal to x squared plus x plus 1. So there is a general way of saying what it means to add up two functions. And these dictionaries are functions in some way, right? They are functions from keys to real numbers. So the question is, can we define, for example, the sum of these two dictionaries? Okay, can we create a data structure made out of dictionaries so that we can sum and subtract the dictionaries? So the idea would be this, that the result of this sum would be a dictionary that maps as follows. Okay, red would be mapped to 2 plus 3, so to 5. Green would be mapped to 1 plus, well, it's missing. So if it's missing, what do we use? If the neutral element with respect to sum, to addition, the element that does not change a number when you add it is 0. So if it's missing, it's as if here, let me write it in gray, we had green, and because it's missing, the value would be the neutral element. Neutral element for plus. If we were multiplying, the neutral element would be 1, right? Multiplying by 1 doesn't change the number. So green is 1 plus 0 and is 1. And blue is, 0 plus 6. And so the sum would be blue 6. Okay? So what I want to create is a class of dictionaries on which we can define arithmetic operations. We consider dictionaries as functions essentially from their key space to numbers, and we want to be able to add, subtract, multiply, and divide dictionaries, okay? Considering them essentially as functions. And the reason we are doing this is that it's really quite instructive in learning how to implement classes, in this case this arithmetic dictionary class, that implement arithmetic operations. And this is something that we will do often in this class. So let's see how to do this in code, okay? How to define a class for these arithmetic dictionaries. As we write the code, here is a small consideration. If I have dictionaries, arithmetic dictionaries rather, D1 and D2, I want to be able to do the following. I want to be able to do D1 plus D2. I want to be able to do D1 minus D2 and so on for the other operations. And I also want to be able to do D1 plus 7 or D1 minus 3. So the right hand side of the arithmetic operator can be either a dictionary, as in these cases here, or a number. Okay, this will be very convenient. So I want this kind of implementation. Let us see how to achieve it. The simple implementation one can do first is this one that I call Mech Arithmetic Dictionary. Mech because it's perhaps not the greatest implementation, but let's start from that. So I don't need to define an initializer. You see, my Mech class inherits from the dictionary class, so you can create these just as you would create a normal dictionary. For example, you can say, let me give you an example. D is equal to Mech Arithmetic Dictionary. This would be an empty one. Let's call it D1, and D2 can be a Mech arithmetic dictionary, and I can initialize it by saying red is equal to 2 and green is equal to 3. In the same way as I can write, dictionary, red is equal to 2 and green is equal to 3, right? So because I inherit, I can do this initialization, and then I can write d1 plus d2, which in this case should be just like d2. So let's see how this works. My implementation, to define the add method, I can do as follows. First, I construct the result. The result is another arithmetic dictionary, right? So I have to create a new one that I will then return. And then I have a problem, that on the right-hand side, I either have a dictionary or I have a constant. So I say the keys of the other dictionary are either really the set of keys if the other one is a dictionary, or else it's an empty set because there are no keys on the right-hand side if it's a constant. In this way, I can compute the total set of keys as the unions of the set of keys of the left and right-hand sides. And I can say the dictionary, the output dictionary for that key is equal to self.getKey0, so the left value, my own value with the default 0, plus, and for the right-hand side I say others.getK0, so I issue the value of k from the dictionary if the right-hand side is indeed a dictionary, and else I will just get the constant. Okay, so I can write these, run it, and check that it works. And I should also be able to write something like d1 plus 3. Well, d1 is the empty dictionary, and d2 plus 3. Okay, so this works. Now, what is not so nice about this implementation is the following. Look at all the code we wrote for add. What is really specific to add and not, say, subtract? Well, only these. Okay? And what is specific of these to addition and subtraction and not, say, multiplication? Well, again, just only this sign as well as the neutral elements. So if I write code in this way, I will have a lot of repeated code. The code for add, subtract, multiply, divide will look very similar. And this is bad in two ways. The trivial way is that, it's just a lot more code. But the less trivial way in which this code is bad is that if I ever make a mistake in one of these methods, like actually before I had a typo in one of these things, I had others here. So if you make a typo or if you make a misjudgment about how to implement these and you need to fix it, then you need to reproduce your fix 4 times. So this is really the drawback of having repeated code. It's not so much that there is more code in front of your eyes, it's that if you have multiple copies of your code, the first time you cut and paste, but then when you fix or improve your code, it becomes very difficult to remember to apply your fix or improvement to all the various copies you have in your code. So I want to teach you how you can factor together this code for addition so that we will be able to specify only the neutral element and the operator and derive all the other operations from it. Okay? So this will be done in our real class. This is how my implementation is. I just implement addition and subtraction. I leave you to have a bit of fun implementing the other operations. But I do as follows. I define this binary op that takes two operands, the left and right operand, an operator, and a neutral element. Okay, and this encodes essentially what we wrote before. So we created the result, we have the set of keys for the left element, the keys for the right element, for the keys in the union of the keys on the right and left. We get the left value and the right value, which is the value in the dictionary if found, the neutral element if not found, and the constant if it's not a dictionary, the left or right operand, right? So I wrote this code in general, quite in general. And then I say that r of k is equal to operator applied to the left value and the right value. Notice that this op is an operator that I'm passing. So I'm passing to this function the two operands, the operator and the neutral value. Notice that this is a static method. It does not use a self. And so I will call it by saying arithmetic dictionary dot binary op. Okay, that's the way you call a static method. And so for sum, or I will pass to it self as the left operand, other as the right operand, and then I need to pass an operator, and I define it on the fly using the lambda notation of Python. I say lambda xy colon x plus y. This is a function that takes a pair xy and returns the sum. This is a very handy trick to be able to build functions on the fly without having to give them a name. If I wanted to give them a name, let me write it and then I will delete it. My code would look much less nice. I would have to say def add self other. Okay? And then I would write something like this. Def op xy return x plus y. Yes, believe it or not, you can nest def. And then I would say return ad.binary op of self, other, op, and 0. Okay, so this would be perhaps more readable to you, but I prefer this notation in which instead of defining op in this funky way, you just define it in a single piece like that. Okay? You could do it either way though. So let me go back to the original definition. So this is better because we have factored together all the complicated code here, and then it becomes very easy to define the various operators. We can see that this works. Okay. I can indeed do these operations between dictionaries. Now, here is a fun thing. Suppose I want to compare the values in a dictionary to a constant. This can be used, for example, to know, do I have at least 2 socks of a certain color, right? So I want to say, can I compute d greater than 2? This will be a dictionary whose entries will be true and false. True for the keys in which I have at least 2 as a value, and false for the keys in which the value is less than 2. So can I define essentially the meaning of the relational operators between dictionaries and constants, or dictionaries and other dictionaries, in fact. And that's quite easy. This is all I need to do. I need to write this code in which I say the implementation of lower than between okay, so perhaps this is a bit fast. Let me write it more slowly. I can write this def arithmetic dictionary lower than between self and other. Okay, this would be a better way to write it, and say that I return. So what is the result? It's ad binary operator between self, other. What is the comparison function? You know, before I would have written, in the case of sum, lambda xy, x plus y, and neutral value 0, right? So before I would have written this code. But here, if this is lower than, what do? Well, I replace this with a lower than. So the way I compare the elements on the left and the right becomes lower than, which produces a boolean as output. Okay? So this would be the more comprehensible version, and then I could have written arithmetic dictionary dot lower than is equal to ADLT. This would be sort of the slow way of doing it. Here I do something crazy. I simply say that ADLT is a function that gets two parameters, so the left and right hand sides, self and other, and returns, and this is exactly this, in which instead of self and other I write left and right. Okay, so this is a super abbreviated way of defining the meaning of these operators. Greater than is equal to a function that takes a left and a right hand sides and return AD binary operator between the left hand side and the right hand side, this lambda function that does the comparison, and the default value which I take to be 0. It's crazily concise, but I let you stare at it so that you can convince yourself that this works. And working it does. For example, I can create this arithmetic dictionary with cat equals 4 and bird equals 2 and check whether it's greater than 2, and the result will be that it's false for bird and it's true for the cat. Okay? So another thing that I want to do is this. We know that in NumPy, or in Python actually, I can ask whether all elements of a series are true, or if any element of a series is true, right? So I can do these. And so I want to be able to do the same for a dictionary. I want to check whether all its entries are true, or if any of its entries are true. Okay? And I can define it in this incredibly concise way. I say arithmetic dictionary.all method is a method that takes self and returns all of self values. Again, the slow definition would have been something like this. Def AD all of self. Okay? And then I would have said return all of self.values. And then I would have had to say ad.all is equal to ad_all. Okay, this would be the normal way of doing it. But using the fact that I can use the lambda notation, I can write it in this super abbreviated way, because I can say ad.all is equal to a method that takes a self and returns all of self.values. It does the same, it just does it in a one-liner. Okay? Here is another method. This is a method that filters only the elements that satisfy a given condition. For example, if I have a dictionary, D, and I give it the condition lambda x is greater than 1, the result of this filtering operation will be only the elements of D for which this condition is true. Okay? Oops, why it doesn't work? Because I think I skipped a crucial line. Yes, okay. And so when this is all done, your challenge for the homework, the real challenge, is essentially this. You have to implement the sock drawer in terms of arithmetic dictionaries. So the idea is this. In our original implementation, we had a sock drawer that inside had a dictionary that was mapping from colors to how many we have, to the number for that particular color. And what I ask you to do now is to replace these. In fact, I give you the beginning of the code to a dictionary D that is an arithmetic dictionary. So your code will look like something like this. Def init of self. Okay, and to create an empty sock drawer, you will have to say something like self.socks is equal to an empty arithmetic dictionary. And the idea is that when you put socks in the dictionary, when you put socks in the drawer, I beg your pardon, what are you doing is that you are adding arithmetic dictionaries. So there is the arithmetic dictionary representing how many socks you have already in the drawer, and there is another arithmetic dictionary that is representing how many socks you are adding. Perhaps, it will be just the arithmetic dictionary saying ready equals to 3, to put in 3 red socks, and you will be simply able to add them together and put the results again in self.socks. To check if you have colors available, you would simply be able to use the above comparisons we define for arithmetic dictionaries and filters in order to check only the colors for which you have at least two elements in the dictionary. So you are able to actually replicate all the operations for which we had to use loops or iteration in the previous implementation simply as operations on arithmetic dictionaries and recreate your implementation of sock drawers. So this is a kind of an interesting conceptual exercise that I leave you to do.